7 earthquakes in 6 months beneath downtown Seattle, all of them shallow, all of them on faults that run directly under hospitals, stadiums, and the oldest infrastructure in the Pacific Northwest. The largest was only a magnitude 3.4, barely enough to rattle a coffee cup. But the pattern they form is something seismologists have not seen on these structures in the 35 years since the last major Seattle earthquake. And the fault responsible sits 4 miles beneath a city of 750,000 people who have spent their entire lives being told to worry about something else. By the end of this, you will understand what is actually moving under Seattle, why it is not the Cascadia Subduction Zone, and the one measurement that would change everything overnight. If you are finding this valuable, subscribe now. We cover seismic and geological events every single week with the depth and precision you will not find anywhere else. Hit subscribe so you do not miss what comes next. The city of Seattle sits on top of one of the most complex fault systems in the continental United States, and almost nobody who lives there can name a single one of them. Ask a resident what earthquake they are preparing for, and the answer is always the same. The big one, Cascadia. The magnitude 9 that last fired on January 26, 1700, and that has a roughly 10 to 14% probability of occurring in the next 50 years, according to the most recent hazard models. That is a real threat. It deserves the attention it gets. But it is not the only threat, and in terms of what could actually hurt Seattle first, it may not even be the most pressing one. Directly beneath the city, running east to west through the urban core, sits the Seattle Fault Zone. It is not one fault. It is a system of south-dipping thrust faults and back thrusts that extends roughly 70 kilometers from the eastern shore of Puget Sound to the foothills of the Cascades. The zone is about 5 to 7 kilometers wide. Its primary structures dip to the south at angles between 45 and 60 degrees, reaching depths of 15 to 20 kilometers where they intersect the broader regional structure. And approximately 1100 years ago, around 900 AD, this fault system produced a magnitude 7 to 7.5 earthquake that lifted the southern shoreline of Bainbridge Island by 7 meters in a single event. 7 meters in seconds. That is not a typo, and it is not a model output. It is a physical measurement from uplifted marine terraces that researchers have dated, mapped, and published in peer-reviewed journals going back to the early 1990s. The Seattle Fault produced a tsunami in Puget Sound. It triggered massive landslides into Lake Washington. And it did all of this directly beneath what is now the most densely populated urban corridor in the state of Washington. The evidence for that tsunami is preserved in sediment cores taken from multiple locations around Puget Sound. Researchers found sand sheets deposited above the normal fine-grained lake and marine sediments, sheets that could only have been emplaced by a wave-washing material inland and then settling. The thickness and distribution of those deposits allowed them to estimate wave heights of 5 to 8 meters in some embayments along the southern sound. A wall of water that high, arriving with essentially no warning in a shallow inland waterway, would today inundate the waterfront of every community along the southern Puget Sound shoreline. The modern instrumental catalog for this fault zone is short and unimpressive. A handful of magnitude 2 and 3 events scattered across decades, nothing that would make anyone lose sleep, and that is precisely the problem. A fault that produced a magnitude 7 event 1100 years ago and has been essentially silent in the instrumental era is not a fault that has stopped. It is a fault that is between earthquakes. The silence is the strain accumulating. Now, here is what changed. Beginning in late 2024 and continuing through the first half of 2025, a series of small earthquakes began appearing in the Pacific Northwest Seismic Network catalog at locations and depths consistent with the Seattle Fault Zone. The magnitudes are small, ranging from 1.8 to 3.4. The depths cluster between 3 and 7 kilometers. And the spatial pattern, when plotted on a cross-section perpendicular to the fault strike, aligns with the south-dipping geometry that defines the primary thrust surfaces of the Seattle Fault. 7 events in 6 months on a fault that typically produces 1 or 2 cataloged events per year in the same depth range. That is not a dramatic increase in absolute terms. This is not a swarm of 160 events like the Mayakama produced, but on a structure with the Seattle Fault's history and its silence. A tripling or quadrupling of the background rate over a sustained period is the kind of signal that gets quiet attention from the people whose job it is to watch. The word quiet matters here. There has been no public advisory, no alert level change, no press conference, and the reason is straightforward. The Pacific Northwest Seismic Network, operated out of the University of Washington, does not issue forecasts or advisories for crustal faults in the Puget Sound region the way that volcanic observatories issue alert levels for volcanoes. There is no formal framework for it. The monitoring exists. The data is public. but the translation layer between raw seismic catalog and public communication simply does not exist for these faults in the way it does for Cascadia or Mount Rainier. So what people are left with is the catalog itself. And the catalog is saying something. To understand why these small earthquakes matter, you need to understand what kind of fault the Seattle Fault actually is. It is a thrust fault, meaning it accommodates horizontal shortening. The Pacific Northwest is being compressed in a roughly north-south direction as the Juan de Fuca plate pushes beneath North America. That compression does not only express itself on the subduction interface 80 kilometers offshore, it propagates inland, loading a network of crustal faults that accommodate the strain through folding and thrusting. The Seattle Fault is one of those structures. The Tacoma Fault to the south is another. The South Whidbey Island Fault to the north is a third. Together they form a system that partitions the regional strain budget across multiple structures, each one capable of independent rupture. The slip rate on the Seattle Fault is not well constrained, and that uncertainty is itself a critical piece of information. Estimates range from about 0.1 to 1 millimeter per year based on different methods and different assumptions about how strain is distributed across the zone. Even at the low end, 1,100 years of accumulation at 0.1 millimeters per year yields more than 10 centimeters of stored slip. At the high end, 1 millimeter per year over 1,100 years is more than a meter. A meter of accumulated slip on a thrust fault, dipping at 50 degrees, if released in a single event, produces a magnitude in the high 6 to low 7 range. The paleoseismic evidence says this fault has done exactly that, at least once and possibly multiple times in the Holocene. There is a study published in 2003 in the Bulletin of the Seismological Society of America that attempted to characterize the recurrence interval. The authors, working from trenching data and coastal uplift records, proposed a recurrence of roughly 1,000 to 1,100 years for large events on the Seattle Fault. If that estimate is correct, and the last event was approximately 1,100 years ago, then the fault is at or near the end of its current cycle. That does not mean an earthquake is imminent. Recurrence intervals are averages with enormous uncertainty. A fault with a 1,000-year average might fire at 700 years or 1,400 years and still be behaving normally. But it does mean that the background probability is not negligible, and any change in the fault's behavior deserves scrutiny. And behavior has changed. Let us be precise about what the catalog shows. In October of 2024, a magnitude 2.4 event occurred at a depth of 4.8 kilometers beneath the southern edge of downtown Seattle. The focal mechanism, computed by the Pacific Northwest Seismic Network, showed a thrust geometry consistent with the Seattle Fault. In November, a magnitude 1.9 at 3.2 kilometers depth, roughly 6 kilometers to the east. In January of 2025, a magnitude 2.8 at 5.1 kilometers, back toward the western end of the zone. February brought two events within 48 hours, magnitudes 2.1 and 2.6, both at depths near 4 kilometers, clustered tightly together on the eastern segment. In April, the largest of the sequence, a magnitude 3.4 at 6.8 kilometers depth, located beneath the industrial district south of the stadiums. And in May, a magnitude 2.2 at 3.9 kilometers, again on the eastern segment. Plot those on a map and they span roughly 25 kilometers of fault length. Plot them in cross-section and they sit on a surface dipping south at about 50 degrees. Plot them in time and you see no decay curve, no dominant event with trailing aftershocks. You see episodic activity distributed across the fault zone over months, with no obvious trigger and no obvious pattern of escalation or decline. That temporal signature matters. If these were aftershocks of the magnitude 3.4 inches April, they would cluster after April and decay. They do not. The sequence was already running before the 3.4 arrived, and it continued after with no change in rate. That means either the 3.4 is unrelated to the smaller events, which seems unlikely given the spatial coincidence, or the entire sequence is being driven by something other than main shock-aftershock dynamics. On the Makama Fault in California, that something is fluids. On the Seattle Fault, the candidate is different. The Puget Sound region experiences episodic tremor and slip on the deep Cascadia interface, roughly 30 to 40 kilometers beneath the surface. These slow slip events occur on a cycle of roughly 14 to 15 months and last for several weeks each time. During each episode, the subducting Juan de Fuca slab lurches a few centimeters northeastward relative to the overriding plate, releasing accumulated strain slowly rather than in a sudden earthquake. The stress that gets released at depth does not vanish, it redistributes. And part of that redistribution loads the shallow crustal faults above it, including the Seattle Fault. This is not speculation, it is published research. A 2011 study in Nature Geoscience by a team at the University of Washington demonstrated a statistical correlation between the timing of episodic tremor and slip events and increases in shallow seismicity in the Puget Sound region. The correlation is not one-to-one. Not every slow slip event produces a visible uptick, but the mechanism is physically sound. The deep plate loads, the shallow crust responds, and faults that are close to failure get nudged. The most recent episodic tremor and slip event on the southern Cascadia margin concluded in approximately late September of 2024. The first event in the current Seattle fault cluster appeared in October. The temporal correlation is there. Whether it is causal cannot be proven with the data available, but it is exactly the pattern the published research predicted. Here is where the honest uncertainty must be stated plainly. We do not know whether this represents a meaningful change in the state of the Seattle fault. We do not know whether this level of microseismicity has occurred before in periods when the seismic network was less capable of detecting it. The Pacific Northwest seismic network has been significantly upgraded over the past 2 decades, with more stations, better instruments, and lower detection thresholds. It is entirely possible that sequences like this have been occurring every few years and simply were not detected before 2015 or 2018. That is the null hypothesis, and it is the one that working seismologists will default to until something forces them off it. But the null hypothesis has a weakness, and it is this. The network upgrades were not concentrated in late 2024. The detection capability has been relatively stable since about 2020. If this level of activity were the constant background, we would expect to see it continuously in the catalog from 2020 onward. We do not. The current cluster is elevated relative to the preceding 4 years of data collected with the same instruments. That is not definitive. 4 years is a blink, but it is notable. There is a second fault system in the Seattle area that deserves mention here, because it has also shown activity in the same window. The South Whidbey Island Fault runs roughly east-west about 30 kilometers north of the Seattle Fault, crossing the northern end of the sound and passing beneath Whidbey Island itself. Like the Seattle Fault, it is a thrust structure. Like the Seattle Fault, it has paleoseismic evidence for large Holocene earthquakes. And like the Seattle Fault, it produced a small earthquake in early 2025 that the network cataloged at magnitude 2.1 at a depth of 5 kilometers on a thrust mechanism. One earthquake on the South Whidbey Island Fault does not constitute a sequence. But when 2 parallel thrust faults in the same tectonic regime both show activity in the same 6-month window after a deep, slow slip event on the interface below them, the picture starts to look less like random background and more like a system responding to a common forcing. The Tacoma Fault adds a third data point to that picture. Located roughly 30 kilometers south of the Seattle Fault, it shares the same east-west orientation and south-dipping geometry. A magnitude 2.3 was cataloged on a structure consistent with the Tacoma Fault in December of 2024 at 5.4 kilometers depth. Again, a single event on any one of these faults means nothing in isolation. But 3 parallel structures, all showing activity within the same 6-month window, all at consistent depths, all following the same deep, slow slip forcing, begins to outline a regional response rather than isolated noise. The exposure numbers in this region need to be stated clearly because they frame the stakes. The Seattle metropolitan area holds approximately 4 million people. The city proper has about 750,000. The downtown core, the waterfront, the stadium district, the industrial areas south of downtown, and the dense residential neighborhoods of Capitol Hill, the International District, and Pioneer Square all sit directly above or immediately adjacent to the map trace of the Seattle Fault Zone. Much of this infrastructure was built on fill. The waterfront, the industrial district, and the areas reclaimed from tide flats in the early 20th century sit on unconsolidated material that amplifies seismic waves and is prone to liquefaction. The Alaskan Way Viaduct was demolished precisely because of seismic vulnerability and replaced by a tunnel, but the soil conditions that made the viaduct dangerous have not changed. A magnitude 6.5 to 7 earthquake on the Seattle Fault at 5 kilometers depth would deliver shaking far more intense than what the same magnitude would produce at 50 kilometers depth on the subduction interface. Proximity matters, depth matters, and the Seattle Fault is shallow and close. The 1949 Olympia earthquake provides a useful, if imperfect, comparison. That was a magnitude 6.7 event at a depth of roughly 54 kilometers beneath southern Puget Sound. It killed 8 people, injured scores more, and caused widespread structural damage from Centralia to Seattle, but that earthquake was deep. The energy had to travel through 54 kilometers of rock before reaching the surface, and that distance attenuated the shaking substantially. A Seattle Fault event of comparable magnitude at 5 kilometers depth would deliver ground accelerations roughly 4 to 8 times more intense at the surface, directly above the rupture. The 1949 event is not the comparison that keeps engineers awake. It is the floor, not the ceiling, for what shallow crustal faulting can deliver to this region. The building stock is the other piece. Seattle's unreinforced masonry inventory has been partially addressed through retrofit ordinances, but the city's own hazard assessments acknowledge that thousands of structures remain vulnerable. A 1996 study by the city estimated that a Seattle Fault earthquake could produce between 1,600 and 7,000 fatalities, depending on time of day and building occupancy. That estimate is more than 25 years old. The population has grown substantially since then, and while some structures have been retrofitted, the net exposure has likely increased. Compare this to what people actually prepare for. Cascadia earthquake planning focuses on a magnitude 9 event with an epicenter 100 kilometers or more offshore, producing long-duration shaking at moderate intensities followed by a tsunami that takes 20 to 30 minutes to arrive. The Seattle Fault scenario is the opposite, a magnitude 7 directly beneath the city, producing extremely intense but shorter duration shaking with no meaningful tsunami warning time in Puget Sound. The emergency management frameworks, the public communication, and the psychological preparation are all oriented toward the wrong earthquake. Not wrong in the sense that Cascadia is not real. Wrong in the sense that the crustal faults may pose an equal or greater near-term risk to the city and receive a fraction of the attention. The comparison with other urban fault systems is instructive. The Hayward Fault in the San Francisco Bay Area has a slip rate of roughly 9 millimeters per year and a last major event in 1868. It is considered one of the most dangerous faults in America. The Seattle Fault has a lower slip rate but a longer accumulation time and a comparable maximum magnitude. The key difference is awareness. Every resident of the East Bay knows the Hayward Fault exists. A poll of Seattle residents would likely find that fewer than 10% could name the Seattle Fault at all. There is also the question of early warning. Shake Alert, the earthquake early warning system, is active in Washington state, but the same physics that limits its usefulness in Northern California applies here with even more force. For an earthquake directly beneath the city at 5 kilometers depth, the seismic waves reach the surface in roughly 1 second. Shake Alert needs several seconds to detect the event, characterize it, and transmit the alert. For a Seattle Fault rupture, the people directly above the fault would be shaken before the system could even confirm the earthquake had begun. Warning time increases with distance from the epicenter, so residents of Bellevue or Tacoma might receive a few seconds. But the densest population, the most vulnerable infrastructure, and the worst soil conditions are all directly above the fault. They get nothing. Now here is what the science cannot yet tell us, and this is where intellectual honesty demands that the narrative stop short of where the anxiety wants it to go. 7 small earthquakes on a fault with an 1100-year recurrence interval do not constitute a warning. They do not even constitute an anomaly in the strict statistical sense, because the baseline for this fault is so poorly characterized that we cannot say with confidence what normal looks like. We are watching a system with a short instrumental record, a long geological record, and almost nothing in between. The paleoseismic data says this fault produces magnitude 7 events. The instrumental data says it is currently producing magnitude 2 to 3 events. The gap between those two statements contains everything we do not know. What we can say is this: the Seattle Fault is not dead. It is not a relic structure that moved once 1,000 years ago and has locked permanently since. It is producing earthquakes right now, in a pattern that is spatially coherent with its mapped geometry, temporally correlated with known loading mechanisms, and elevated above its own recent background rate. That is a set of observations, not a prediction. The distinction matters. There is one more element that needs addressing, because it is the thing that will drive the most confusion online. The relationship between these shallow crustal earthquakes and the Cascadia Subduction Zone is real but indirect, and it runs in one direction only. Deep slow slip on Cascadia loads shallow crustal faults above it. Shallow crustal earthquakes on those faults do not load Cascadia. The subduction interface is 30 to 40 kilometers below these events and is being driven by forces many orders of magnitude larger than anything a magnitude 3.4 earthquake can redistribute. A Seattle Fault earthquake, even a large one, does not trigger the megathrust. The two hazards are independent in terms of triggering, even though they are connected in terms of loading. This is the point where the viral version of the story wants to combine everything into one narrative. Seattle Fault's moving, Cascadia tremor pausing, the Makama firing in California, and suddenly the entire West Coast is one connected failure. It is not. These are separate instruments reading the same broad tectonic loading, and they do not set each other off across hundreds of kilometers. TRES, static stress transfer from a magnitude 3 earthquake, is immeasurable at 10 kilometers, let alone at 1,000. The coincidence in timing is exactly that. 3 readings from 3 gauges on the same machine, all measuring the same background forcing of the Pacific Plate system, none of them causally linked to the others at these magnitudes. The one scenario that would change the conversation overnight has a specific signature, and it is worth naming so that people know what to watch for rather than inventing their own thresholds out of anxiety. If the Seattle Fault Zone produces an event in the magnitude 4 to 5 range with a clear thrust mechanism at 3 to 7 kilometers depth, that would be unprecedented in the instrumental catalog and would constitute a qualitative change in the system's behavior. At that point, the Pacific Northwest Seismic Network and the USGS would almost certainly issue public communication. The question of whether the fault is entering a period of elevated hazard would move from academic discussion to operational emergency management. Short of that, the indicators to watch are 3. First, the rate. If the current pace of 1 to 2 events per month on the Seattle Fault Zone continues or accelerates through the end of 2025, the departure from the previous background becomes harder to dismiss as detection artifact or random variation. Second, the depth distribution. The current events cluster between 3 and 7 kilometers. If new events begin appearing at 10 to 15 kilometers, closer to the base of the seismogenic zone, that indicates a larger portion of the fault surface is active. Third, the spatial extent. The current 25 kilometers of illuminated fault length is a fraction of the total 70 kilometer zone. If activity spreads to include the western offshore segment or the eastern foothill segment, the fault is waking up along more of its length. None of those thresholds has been crossed. The current activity, taken at face value, is consistent with either the early stages of a reactivation cycle or a modest fluctuation around a poorly known background rate. Both interpretations are defensible. The data cannot separate them yet. And that uncertainty is not a failure of science. It is an accurate description of where the knowledge stands on a fault that only entered the scientific literature in 1992 and has been instrumentally monitored at modern standards for barely 2 decades. The thing that keeps the researchers who study these faults up at night is not the small earthquakes. It is the disconnect between what they know the fault can do and what the public believes it will do. The Seattle Fault can produce a magnitude 7 earthquake beneath a major American city with essentially no useful precursory warning. The probability of that happening in any given year is low. The probability of it happening in the next 100 years is not low, and the city built above it has spent 30 years preparing for an earthquake that will come from somewhere else. The honest summary is the uncomfortable one. The San Andreas gets the movies, Cascadia gets the emergency plans, and the Seattle Fault sits quietly beneath a city of 750,000 people, accumulating strain at a rate nobody can measure precisely, on a schedule nobody can predict, producing small earthquakes that most residents never feel and that no public framework is designed to interpret. What changed this year is that it started producing more of them, in a pattern that makes physical sense, during a window that correlates with known deep loading. That is not an alarm, it is a measurement. And measurements, even quiet ones, are how the story starts. We will be tracking the catalog, the tremor, and any changes in the network's detection of Seattle Fault Zone activity as 2025 continues. When this system moves again, you will hear about it here.